back to the gas laws. So last week, we made gas bags, which was kind of fun. We filled up, what was the gas that we used to fill up the bags last week? Anyone remember what it was? What was the gas we produced that filled up the bags? Feel free to unmute and say something. Remember, we had sodium bicarbonate and acetic acid. What gas was produced when we mixed them together?
CO2.
That's right, carbon dioxide. We made carbon dioxide last week. What gas are we going to make this week?
Oxygen.
That's right, we're going to produce oxygen gas. So, yeah, looking forward to that. So again, we're going to be dealing with the gas laws. So hopefully everyone's sort of quite familiar with our good friend Pivnert at this point. Let me annotate here. Mr. Pivnert, Mr. PVNRT. So we measure gases with four different, you take four different measurements. We measure its pressure, we measure its volume, we measure how many moles of gas we have, and we measure the temperature. And then remember, we have a constant that relates all of those things together. And that's what you're going to do tonight. You're actually going to calculate the value of R. So we kind of much know what the value of R is. And so hopefully we're going to get fairly close, you know, fingers crossed. And so, as is mentioned, this is the ideal gas law. And an ideal gas, I guess you sort of, that was one of the questions tonight. No, it can't go through walls. An ideal gas basically means that it doesn't interact with each other. The gas molecules are completely independent of one another. They don't have any interactions, and they just spend all their time flying around in straight lines and bouncing off each other and off the cylinder. And helium comes about as close to ideal gas as we can possibly get. But even helium, under like extreme pressure, interacts with other helium molecules or atoms slightly. Not very much, but slightly. But most simple gases, like small gases like O2 and N2, and not quite, CO2 isn't quite ideal because it's very polar. It has some polar properties. But most gases are pretty ideal and have a linear relationship between P and V and N and T. And so we're going to try and figure that out tonight. So the law that we're going to be dealing with is good old Avogadro's law. So what we're going to do is measure the volume of a gas. So here, just basically a container that doesn't have any gas in it. And then we put gas into it, and the volume that it takes up is directly proportional to the molar amount of gas. So what we're going to do is generate moles of gas. We're going to generate moles of oxygen gas. And then we're going to measure the volume that oxygen gas takes up. And we're going to see what the relationship is between the number of moles of oxygen we produce and the volume it produces. And will we be changing the temperature or the pressure during this lab?
The pressure?
How are we going to change the pressure?
By squeezing on something.
What are we going to be squeezing, man? I don't recall squeezing in the lab instructions. I'm not going to be squeezing anything. No, we're not changing the pressure. So what will the pressure be? So since to determine the value of R, we need to know P and V and N and T. So we're going to measure the volume. We're going to calculate the number of moles, and we're going to measure the temperature. How are we going to measure the pressure? What's the pressure going to be? When you're filling up the gas, when you're filling up that upside down graduated cylinder with gas, what's going to be the pressure inside the cylinder?
Are we using the gas constant?
No, we're not, because you're going to be calculating the gas constant. We need to know what the pressure is. How are we going to determine what the pressure is? How do we measure the pressure inside that inverted graduated cylinder? Because we need it. We need to have that pressure in order to measure R. How are we going to figure that out? What's that pressure going to be equal to? The pressure of the gas inside that cylinder, inside our graduated cylinder, is going to be the same as the pressure of what else?
On the outside of it?
There you go. Exactly. It's going to be the pressure inside the room. And so we can pretty much assume that the atmospheric pressure is going to be around 1 atmosphere, because that's generally the pressure. It's going to be pretty darn close. If you really want to get accurate, you can look up, like we did last week, and see what the pressure is wherever you are. But it's going to be pretty close to 1 atmosphere. So it'll be like 0.995 to like 1.005. It'll be really, really close. So since we're not squeezing the cylinder and we're not expanding the cylinder, the pressure inside the cylinder will be exactly the same as the pressure outside of it. So we can just assume that it's going to be around 1 atmosphere. So since we know P, we're going to measure V, we're going to determine N, and we're going to measure T. We have all the information we need to determine what R is supposed to be. So as we remember that since the volume of gases are dependent on the mole of gases, that means that no matter what the gas is, 1 mole is going to take up the same volume. And this is true. For 1 mole, we can see that no matter, we have 3 different gases here. We have helium here, and then we have nitrogen, and here we have oxygen. And so it doesn't matter that helium and oxygen are different masses. Helium has a mass of 2, right? 2 grams per mole. Oxygen has a mass of 32 grams per mole. But they take up the same volume. And the reason is there is so much, the vast majority of space inside a cylinder is basically empty. Seems weird to say that, right? But I mean, the vast, like 99.9999% of the space inside a cylinder has nothing in it, because the distance between gas molecules is enormous. So basically, most of the time, there's nothing in there, and then there's gas molecules moving around. So it doesn't really matter how big the gas molecules are. They're so big that they all take up about the same amount of space. So you can see that the densities are different. The densities are different because the mass of 1 mole of helium is 16 times less than the mass of 1 mole of oxygen. So the densities are going to be a lot different, but the amount of space they all take up is going to be exactly the same. So we're going to use that to our advantage. So again, here's our good old friend Pivnert. And so what we're going to be doing is determining what R is. And so what we want to do here is figure out a way to plot a change. So, oops. And when we plot a change, that means delta, right? We're going to be looking at the relationship between delta V and delta N. So as we change the number of moles, what's going to be the change in the volume? So basically, we're going to be using some arrangement of this particular mathematical equation to figure out what R is. If P stays the same and R stays the same, you can see that we have a direct relationship between V and N. And that's exactly what we're going to be doing. So what we're looking at is V should be equal to NR if we plot moles versus volume. So the slope of that line should be R, okay? So here's our setup. So as I mentioned, we're going to be sort of, make a bit of a mess tonight. So it's a good idea to put all of this stuff in I brought a pie tin down to put it in, but just like, either have it on a towel or something that can hold water, because we're going to be, splashing water around. So what we want to do is fill our 50 mil graduated cylinder with water. And then we're going to put this tube into it, turn it upside down, and then place the whole thing into our 250 mil beaker, which is also filled with water. We basically want it all to be filled with water because we want the gas to displace the liquid. So as the gas is being produced in here, so we're going to be producing oxygen gas in there. It's going to bubble up, go through the tube, and then displace the water. This should be filled with water. And then the water gets pushed down as the gas fills up. And then we'll just measure the volume from here to here. We'll see how much volume of gas is made. And this is the reaction. So everyone's probably familiar with hydrogen peroxide. You use it basically to clean out wounds. And the reason why it's good for that is because it makes a radical. I don't know, have we discussed radicals before? Radical atoms? Or is this a new concept?
I think it's new.
Oh, okay. Well, I won't get into it too much, but basically, a radical is just an atom with an odd number of electrons. So when we're making our Lewis structures and everything, right? Have you noticed that pretty much every time you make a Lewis structure, everybody has an even number of electrons? Like they have 4 or 6 or 8 or 10 or 12 or 2 or something. It's always an even number because lone pairs come in pairs and bonds are a pair of electrons. So it's always in pairs. Well, a radical is missing 1 electron, just 1. And so they're extremely reactive. Basically, they go through, tearing through everything, looking for another electron. And since oxygen is the one carrying this lack of electrons, that is what hydroxyl would look like with one missing. So this oxygen has 7 electrons, and it's supposed to have 8, right? It's supposed to have a full octet. It's only got 7. So since oxygen is super electronegative, it likes to steal electrons from other elements, that will go through basically stealing electrons from everything. And basically it will kill anything, destroy any tissue, anything around that doesn't have the ability to stop it. And so what animals, bacteria, different cells have evolved is a way to get rid of it. And the way to get rid of it is with this enzyme called catalase. One of the very first enzymes discovered, catalase. And what it does is it takes 2 hydrogen peroxides and reacts them together to release 2 moles of water and a mole of oxygen gas, which is much better than having peroxide around, because peroxide, as I mentioned, forms these radicals and basically just destroys everything in sight. And so if you don't have one of these around, you get wiped out. Basically, it just takes all your electrons away and wipes you out. So one organism that does have, I mean, you have this enzyme in you, another organism that has this enzyme is yeast. So what we're going to do is take a little bit of yeast and introduce it to some hydrogen peroxide, and then it should pretty much instantaneously turn it into water and oxygen. So it's very, very fast. Like 1 molecule of this catalase enzyme can cause like billions of atoms or molecules of O2 to be released in seconds. So it's a very, very, very fast reaction. So the reaction should be over fairly quickly, meaning when we have our little bit of yeast in there and we add our peroxide, we've got to make sure that we put the cap down like immediately, or because it's going to start producing oxygen super, super, super fast. So that's our reaction. Note that there is a molar relationship between the number of moles of peroxide and oxygen. What's the molar relationship between the peroxide and the oxygen gas being produced?
Two to one.
So what does that mean? Two of what to 1 of what?
2 hydrogen peroxides to 1 oxygen gas.
Right. So when you add different amounts of hydrogen peroxide, you're going to need to determine the moles of hydrogen peroxide that are present, and then half of that number will be moles of oxygen gas. Okay, so that's how we're going to determine how many moles of oxygen gas we have. So here's our relationship, PV nRT again. So here's here's how we're going to do the activity. So you have a thermometer. So we're going to need the air temperature where you are. So that number is going to be different for everybody, slightly different. Like here, I think it's around 15. It's usually 15 degrees Celsius. And then what temperature are you going to use when you do your calculations? Are you going to use Celsius, Fahrenheit, or Kelvin?
Kelvin?
Kelvin. We always use Kelvin with gas. Always, always, always. Excellent. So we fill our graduated cylinder with water. We fill the beaker with water. We have, now what you should do is take, hang on, I'll be right back. So with the kit, you can see that we have this tube. So a tube about yay long, as it turns out. So what you want to do is take this and sort of push it into one end of the tube. Make sure that that's on good and tight, because the last thing we want is for this to pop off in the middle of the experiment. And, you know, just having that dangerous oxygen gas all over the place. We wouldn't want that. So yeah, make sure that this is good on, good and tight. So then, if you have King Kong thumbs like I do, so we're going to fill up our graduated cylinder with water, put this tube in, put your thumb over the whole thing and turn it upside down. So if you haven't got big ass thumbs, I don't know what you're to do, but you know, use 2 fingers or something, a thumb and another finger, or 2 thumbs, whatever. Turn it upside down, put it under the water in the 250 ml beaker, and then let go. And then this will be coming out, and we're going to be putting this into the little bottle where we're going to put our yeast and our hydrogen peroxide. So if it's not completely empty, I mean, if it's not completely filled with water, there's going to be some volume on here. Let's say it's like 5 mils or something. Well, let's write down 5 mils is the initial volume, and the initial volume will be 5 mils of air. And then whatever additional volume you add from the O2, we'll count that as your volume of oxygen. So if you collect 20 mils, subtract the 5 of the air that was already there, and you've got 15 mils, okay? So then we're going to measure out a really tiny amount of yeast, like 0.1 grams of yeast. So is it important that we get the 0.1 grams really accurate? Yes or no? Of yeast. Is it important we get exactly the right amount of yeast? What do you think? What's the yeast doing for us? Is it part of the reaction? Like when we balance this reaction, is yeast a part of it? What if we weigh like 0.2 grams of yeast? Is our experiment ruined? Do we have to start over? What do you think? Is it important we get that mass like exactly right? No one wants to guess?
No, it's not important.
You sound so sure of yourself. Why is it not important? I'll put it, you're right. It isn't terribly important that we get exactly 0.1. That's why it doesn't say 0.10 or 0.100. It just says 0.1. Meaning anything from like 0.05 to 0.14 grams is fine. That's a lot of leeway. But why isn't it important? So that was a good guess, huh?
Yeah.
Well, sometimes it's better to be lucky than good. Yeah, the reason it's not important is because you're adding an enzyme. So the enzyme doesn't actually affect the overall reaction. It makes it go faster, but it doesn't affect the overall reaction. You're still going to convert 2 moles of hydrogen peroxide into 1 mole of oxygen gas. You're just going to do it faster. And the enzyme catalase works so fast that if you put twice as much enzyme in, it probably won't make any difference. So that's why it's not terribly important. The amount of catalyst isn't nearly as important as just having the catalyst there, because most catalysts work so quickly that just the tiniest amount of them is sufficient. And so that's why just a small amount, basically we could just add a pinch of yeast and that would be fine. So we put the yeast into our little bottle and then measure 1 mil. And this is what you're going to want to get. This one you will want to get accurate. 1 mil of hydrogen peroxide. And notice it says record the exact volume. So if you have 1.1 mils, record that. If you have 1.0 mils, record that. If it's 1.2, record that. Make sure you get it precise. Precision is more important than accuracy here. So if it's not exactly 1 mil, that's fine. If it's 0.9 mils, that's fine. But make sure you precisely measure the volume, because we're going to convert that volume eventually to moles and then relate it to the volume. Then we put the peroxide in, and then we snap this top on as quickly as we possibly can, and let the gas start collecting into the graduated cylinder. And then we're going to repeat it again with 1 mil. So we're going to do 2 runs with 1 mil each, and then two runs with 2 mils, 2 runs with 3 mils, 2 runs with 4 mils, for a total of 8 runs. And so keep track of the air temperature every time. It might change. Just me being in this room is changing the air temperature slightly. So it's going to get warmer the longer I'm in here breathing and giving off heat. Measure the volume, our initial volume of gas, final volume of gas, and exactly how much oxygen is being produced, okay? Then we're going to have to figure out how much hydrogen peroxide there actually is, right? So this is basically after you've finished. We're going to need to calculate the molarity of 3% hydrogen peroxide. And 3%, I believe it is, I'm going to make sure it's, just says 3%. So we have to assume that it is 3% by mass. Meaning for every 100 grams of this, 3 grams of it is going to be hydrogen peroxide. So we're going to assume that the density, since it's 99% water, we'll assume the density is going to be 1 gram per mil. So 1 mil is 1 gram. So we'll have 1 gram of solution. 3% of that will be hydrogen peroxide. So in other words, 0.03 grams will be hydrogen peroxide. The molar mass of hydrogen peroxide is this, and then you figure out how many moles of hydrogen peroxide you have, okay? So you'll have moles of hydrogen peroxide, you'll have your volume of oxygen produced, and so you're going to be graphing this. Now, what are we going to plot? What goes on the x-axis here? Whoops. What goes on the x-axis and what goes on the y-axis. So what are we going to put on the x-axis here? Is that the dependent variable or the independent variable? Do you remember the difference? What's the difference between the independent variable and the dependent variable? We put the dependent variable on the x-axis, and we put the independent variable on the y-axis. So in this situation, what are we going to put on the dependent axis, dependent variable? Which one is the dependent variable? Because we're going to be two things. We have moles of O2. We're going to calculate that. And we have volume of O2. Which one is the dependent variable? Which one is the oh, sorry, even I screwed that up. I get this wrong all the time myself. I apologize. Independent variable goes on the bottom. Gah. See how easy it is to screw it up. So independent on the bottom, dependent on the y-axis. So which one is the independent variable?
Is volume on the y-axis?
Mm-hmm. It is. Why is that?
Because that depends on what the number of moles is.
Bingo. Exactly right. The independent variable is the one we can independently vary. And that's what we're doing. We're adding 1, 2, 3, 4 mils. We could add half, 1.5, 2.5, 3.5. But we're not going to do that. We're going to do 1, 2, 3, and 4. We can independently vary it to whatever we want. The y-axis, the dependent, is dependent on how much hydrogen peroxide we use. It can't vary only depending on the amount of hydrogen peroxide we use. So it depends on what we choose for the hydrogen peroxide. So moles of O2 go down here, and the volume of the O2 goes down here. So we're going to get, so we'll make some points. So here's some points. And then we're going to put a straight line through them. What's going to be the slope of that line? What is going to relate moles to volume? What's the relationship between, and remember, PV is equal to nRT. So if I put N on the bottom, N all by itself is going to be PV divided by RT. So what's the slope of this line going to be? So remember, a slope of a line is y equals mx plus b. So in this instance, y is n. And then V, I'm sorry, it's the other way around. If we want to, V will be equal to nRT divided by P. Sorry about that. So if Y is volume and X is N, what is the slope of the line? So basically, take N out of nRT divided by P. What are we multiplying N by? In this right here, what are we multiplying N by? To get volume.
RT over P.
Couldn't have said it better myself. Exactly right. Yeah, that's what we're doing. We are, basically all you have to do is just rearrange Pivnert, the ideal gas law, and that's all we're doing here. It's just we're just rearranging it to see what the relationship is between volume and N. And so if V equals nRT divided by P, that means if I plot N versus V, the slope of my line will be whatever it is I'm multiplying N by, and that is RT divided by P. So that's why you need to have the temperature and the pressure. The pressure is going to be basically 1 atmosphere. I don't know what your temperature will be, but if you take the slope of the line and multiply it by T divided by P, your answer is R. So the slope basically gives you R. And that's how you're going to calculate it. Any questions about that? I'm sorry, I made it more confusing than I meant to because I screwed it up because I'm kind of stupid sometimes and it's late. So that's how you do that. Okay. Just rearrange the ideal gas law. That's why I love the ideal gas. We can just rearrange it any old way we want. And we can solve for P, we can solve for V, we can solve for N, we can solve for R, we can solve for T, we can solve for any of them we want. As long as we know all four. And in this instance, we do know all four. We've measured the temperature, we've measured the pressure. We're calculating the number of moles, and we're measuring the volume. So we have all the things we need to determine what R is. And by plotting it, we'll get a better, we should reduce some of the errors because we'll should be able to make a fairly straight line with all these different values. So any questions on how you're going to determine the value of R here? If you do, let me know. I mean, send me a note, come to group meeting. Someone will come to group meeting someday and it'll be a miracle. But yeah, this is basically how you go about that. So let's get started, shall we? Are there any questions about actually doing the experiment before we get going? Everyone's so quiet.
No.
It seems pretty straightforward, right? It'll be fun. Lots of be super messy too. So I'll give everyone about 5 or 10 minutes to get everything ready. I'm going to get ready here, and then we'll come back. Cameras on for those of you who can, and I'll do the first couple with you, and then you can do the rest on your own. Okay? So come back in about, let's say we'll come back at 5 after 8, and we'll get going on the experiment, okay? All right, I will see you in 10. Okay, everyone got all their stuff together? Still not seeing any Chem. Oh. Oh, yeah. Hey, Rachel. Okay, gonna make it. Just gonna make a big ass mess. There's just no way around it. So. Okay. Ooh. Come on, only Rachel and Brandon have come out to play. Come on. Yeah, it's going to be tricky to get this tube in there. Yeah, so if you have any gas bubbles on the side, just tap it. Oh, here we go. Here's scissors, that'll do. Tube in there. Yeah, so it's probably a good idea to have, you see I've got this big pie dish here. Something that's gonna, because this is gonna splash everywhere. So what do you want to do the experiment in the bathroom tonight for some? So basically just fill up the 50 mil graduated cylinder, basically till it's overflowing. You see, I've got it filled up to the very top and then some. Put my thumb over it and then try and quickly turn it upside down and put it underneath the water. Not going to be easy to do. Oh man, I did a particularly poor job there. I'm going to try that again. I had about 10 mils of gas left over. Try that again. All right, better this time. Much better this time. Yeah, I think the secret is when you have your thumb over the top, make sure you get it under the water in the beaker before you let go of it. So I sort of did it at the same time the first time, and a whole bunch of water came spilling out. Now you can see it's filled all the way to the top with water, which is perfect. So that is what we want. I'm going to measure my itty bitty bit of yeast. It's not going to be a whole, not very much. Yeah, like I said, pretty much anything between 0.05 and 0.015 is fine. If you have too much in there, it's not really going to be an issue. There we go. Yeah, I overdid it. Like, wow, I overshot it a bunch. Okay. There we go. And remember, you can, this folds. So when you folds like that, so it makes it putting into a small container much easier to do. Because it's not a very big opening.
So do we put the tube in this beaker and then we put our thumb over it, right?
Right, yes. Yeah, that's the tricky part. It's like, yeah, you put your thumb, you put the tube in it, and then you have to put your thumb over both the tube and the opening. So yeah, it's a little tricky. Okay. Yes, you can see you just get like basically it's a tiny bit of yeast in the bottom of this thing. That's really all you need.
What do we do with the other side of the tube, the one that we're holding?
Oh, that just comes out. And this is what we're going to attach to the top of this. As soon as we add the hydrogen peroxide, we're going to snap this end up onto the top of this 15 mil tube.
Oh, I don't have to put this on it?
Oh, yes, 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 yes.
Okay.
Yeah, so that goes on the other end. Yeah, make sure you push it on good and tight, because we don't want that coming loose.
Are we doing it twice for like each?
Doing them all twice. Yeah, so do two runs with 1 mil, 2 runs with 2 mil, 2 runs with 3, 2 runs with 4. So for a total of 8. But you'll see, I mean, these go by really fast, because since this is a catalyzed reaction, it should take maybe a minute, 2 minutes for each run. Mostly the time will be spent cleaning up the mess afterwards. Yeah, make sure you've got 3%. Sometimes I've seen bottles of 5%. If it's 5%, that's fine. Just make sure you notice this. But I think they're all 3%. Oh, yeah, that's way too much. Oh, I forgot to bring. What would be a good idea is to have a transfer pipette for this. I forgot to bring one. It's upstairs. Anyway, yeah, a transfer pipette. You remember with the little squeeze bottle, squeeze bulbs on the top? Use one of those to transfer liquid from the bottle of peroxide to the 10 mil cylinder, or else you're just going to be pouring it back and forth and back and forth and back and forth. Yeah, I neglected to consider that. I don't have one with me. There we go. So I have got 1.85 mils. So I went over 1. So remember, it's really important when you're measuring to measure this volume. This volume needs to be accurate. The volume of your hydrogen peroxide, that needs to be accurate. And the volume of the gas needs to be accurate. So both those things need to be as accurate as possible. You're going to want 3 significant digits for each one. So instead of like 1 mil, if it's 1.05 mils, write that down. Because the R, you can see, is a really, really small number. So just even small changes, small little errors will make a big difference. How'd that go for you, Anna? Did you get it all filled up? Is there a big air bubble in that, Anna? I can't really tell. Looks good. Oh, you started the reaction already. Sweet. I'm just going to start mine now. Oh, there we go. Cool. You should see that I've got bubbles going here. You can always just give it a shake. But my 15 mil tube is fizzing like crazy, as it should be. And you can see that the oxygen gas is displacing the water. I love doing gas experiments. They're just just sort of just keep tapping the bottle. You want to make sure that all of the hydrogen peroxide is like falling down from the sides of the container and is at the bottom where the yeast is. So you can give it a tap. This thing's been going for about 2 minutes. And it looks like it's pretty much done. How long did yours go, Anna? Mine seemed to go for about maybe 2 minutes, then it stopped. Is it about the same for you?
Yeah, it's about the same.
Yeah. That's the cool thing about the having an enzyme present, having an enzyme to catalyze the reaction, is that it happens super fast. So, and then when we want to measure the volume of the gas, of course, we can't tip this upside down, right? Because then all the gas will come out. So we basically have to sneak around from the side and read the volume. So for me, let's see what we got here. It's hard to read with the goggles on. Oh, here we go. So 5, 10, 15. 15.5 mils. So I had slightly less than 2 mils or 2 mils of hydrogen peroxide, about 1.8 mils. And I got 15.5 mils of O2 gas. What volume did you get, Anna, for your, did you have 1 mil of hydrogen peroxide?
I'm still trying to read it right now. I can't really see.
It's tricky, right? Yeah.
Yeah.
You can lift it up as long as it doesn't break the surface of the water. And you can always just add more water to the 250.
Is it okay if we use 2 sig figs?
Your volume of gas should have 3,
Oh, okay.
right?
Are we supposed to just be squeezing the little bottle?
You don't have to squeeze it, just because if we squeeze it, we change the pressure. So we don't want to change, we want to make sure that the pressure in this bottle and in the cylinder is the same. So we don't need to squeeze it. Just give it a shake, give it a tap, just make sure that the reaction's over. It stopped bubbling, so yeah, my reaction's done. And then we just rinse it out with some water and do it again. So I'll just make a note of. Okay. Yeah, so hopefully you have some place to dump this. And then you're going to want to wash it out a couple times. Make sure. If there's a little water left in it, it doesn't matter. The water's not going to interfere with the reaction, because most of the hydrogen peroxide is water anyway, so. There we go. Man, where'd everybody go? Sadie, you not playing with us tonight?
I was just getting a bowl to dump the water out in.
Yeah. Yeah, I'm glad I brought the pie dish down, because yeah, this is, I think it's not even a towel is going to be sufficient, because there's a ton of water. How are people doing with getting their thumb over it and putting it underwater? Has that been tricky for people to do?
It was kind of tricky for me because my thumb's pretty small.
Yes, well, as you can see, I don't have delicate little digits here, so probably a little easier for me to do. Yeah, I might figure out a way, I don't know, maybe to cover it with like a piece of saran or something like that. Might be easier. Cover it with saran and then turn it upside down and put it underneath. That might be a better way to do it. You might want to try that. Because even if you, like a little comes out, it's fine. Like 1 or 2 mils, 3 mil, that's fine. But if half of it dumps out, then it makes it real tough to measure the amount of O2. Yeah, you can see that this enzyme is pretty tough because these yeast have been dried for who knows how long. And the enzyme's still super active, so. It's the sort of enzyme you would want to be pretty tough. It's too much. Ooh, nice, 3 right on the button. There we go. So 3 mils of peroxide, the reaction is happening a little bit faster than it did last time, which makes a little bit of sense. Although I wouldn't have expected it to be this big of a difference. So what's been about the volume, now that we've all sort of done one, what's been the average volume for 1 mil of hydrogen peroxide? There's a little over 5 mils of gas. Megan, you're not wearing your goggles. Thank you. You wouldn't want to get yeast eye, would you? I mean, come on. I'd never forgive myself if he came down with a case of yeast eye. I mean, we are playing with peroxide, so you definitely wouldn't want to get that in your eye. All right. So for 3, and 25, 6, 28. So I figured I would do, like, I don't know, 3 or 4 of these and then try and construct the graph. Does that sound like a good idea? So everyone get an idea of how to do the graph? Rachel hasn't got her goggles on either. Shame on Rachel.
I spilled water everywhere, so I was cleaning it up.
Oh man, 15 degrees on the button. Starting to smell yeasty. Oh, so what did people get for 1 mil? What's their average value so far? I sort of want to compare it to what I'm doing. What'd you get, Megan, for one mil?
6.
6 mils of gas? That sounds about right. What about you, Brandon? Couldn't hear you. What was it?
Around 5.
Oh, okay, cool. Because man, yeah, if we took like everyone in the class's numbers, you could probably get a really good plot out of that. There'd be so many points on it that it would probably be fairly accurate.
Ewa, bicicleta.
All right, I think we're done here. $20, $30, 36.0. Who's got the lovely singing voice? I think Brandon's serenading us tonight, which is lovely. Was that you singing, Brandon?
Hmm?
Was that you singing?
No.
No. Someone had a lovely voice. Now I want it back. I only sing in the shower and in my car. I'm a sucker for singing in my car, I got to admit. It's embarrassing to pull up to a stoplight and you're just belting something out. Oh, Rachel, are you gonna try that saran wrap trick? If you try it, let me know how it works.
I got it without the saran wrap the second time.
Oh, cool.
I don't know, it gave me a pretty good reaction, so.
Yeah, I think the secret is to fill the beaker like pretty much all the way to the top. Because if it's not filled to the top, it's really hard to get your thumb in there. There we go. Oh, I got an air bubble this time. All right, I'll have to subtract 2. As you can see, having 20 grams of yeast is kind of overkill for this. Because you can use the rest to, bake some rolls or something. One knows. Yeah, it really helps you when you're trying to read the volume of these. If you could hold them against like a dark surface, it makes it much easier to read. Because man, I've got all this white surrounding me and I'm trying to read white numbers. It's really hard. But if you have like a black surface like I've got behind me, it makes it so much easier. 9.6. Yeah, so remember to try and keep the mixture mixing as you're going. Just sort of, I just like to give it a little tap like this. Keeps it going. Yeah, just when you think it's done, just give it a few more taps just to be absolutely certain. This looks like it is toast. No, not getting any more bubbles. Okay. Oh man, got a bunch of gas this time. Nope, still getting a few bubbles. Yeah, I can see why they want us to stop at 4 mils because I put in a little over 5 and it's almost filled the tube entirely. So I think if you went to 6 mils, it would be more than 50 mils of gas. Actually, it is. It's more than 50. Oops. All right. So the lesson there, don't use more than 5 mils. Okay. So the folks off camera, you're not running the experiment tonight? Are you planning on doing it later, or what gives? I know that at least one of you doesn't have a camera that works, but everybody else should. Now the office smells of yeast. Lovely. All right, I'm going to start working on the calculations. I'll be right back. Okay, so even if you just keep working on your experiments. Since this is being recorded, I'll just put it up on the YouTube page in case you can't follow along. What I figured I would do is sort of go over how do we take this data and convert it into something we can plot. So I did 4 reactions, and so I have 1.8 mils, 3.0, 3.65, and 5.60. So that was the amount of H2O2 I had. So we need to convert that to moles. So how do we do that? So we know that it's 3% by mass, H2O2. So we're going to assume that in my 1.8 mils of hydrogen peroxide, I also have 1.8 grams, because the density of water, as we all know, is 1 gram per ml. So if I have 1 ml, I got 1 gram. So that's fudging it a little bit, but I mean, the difference is going to be really, 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 really small. So I have 1.8 grams of hydrogen peroxide solution. Now, 3% of that mass is hydrogen peroxide. So we just multiply that by 0.03, sorry. That gives us our mass of hydrogen peroxide. So 0.054 grams of H2O2. Now, grams aren't going to help me because, remember, it's not a gram of gas doesn't take up a certain volume. A mole of gas takes up a certain volume. So I need to convert that to moles. And the information we're given is that H2O2 is 34.01 grams per ml. So remember, I'm a stickler about this because I make a lot of stupid mistakes, as you could see from my opening remarks. I always leave the units in when I do a calculation. That way I make sure that I'm multiplying when I should be multiplying and dividing when I should be dividing. Because believe me, I make more dumb mistakes in one day than you guys probably make for weeks. So, oops. So I've got 0.054 grams, and I want to always multiply, never divide, always multiply, right? And I want, mole, per mole, per mil, per mole. I want moles, so I'm going to put moles on the top. 1 mole of H2O2 is 34.01 grams. That way I cancel my grams. I'm left with the units of moles. That's what I want. So 34.01. So that is 0.001588. 1588. Now, I wouldn't report 0.1588 moles as a result because that is too many significant digits. I really should have only 2, right? Because I should have only 1 because it's 3%. So I have 2 significant digits in my mass. I really only have 1 significant digit here. But if I round everything to just 1 significant digit, I'm going to have huge errors in my calculations. So what I will do is I will carry over as many significant digits as I want during the calculations. And then when I get to the very end, I'll round to the right significant digit. So when I get to the calculation of R, I'll round to 2 significant digits, but I'm not going to start rounding first. That's a way of introducing a lot of error that you don't want, because you're taking information and you're changing it, right? You're changing it before you do your calculations. And so you're starting with, basically you're starting with impaired numbers. You're starting with numbers that have already had some sort of function done to them. You don't want to do that. So don't do any rounding till you get to the end. It's one of the major sources of error I notice in chemistry students' calculations is doing that. They will measure mass to 4 significant digits, and then they will round to 1 and then do a calculation. That doesn't make any sense. So that's how many moles of hydrogen peroxide I have. And that's really all I want, is to plot moles versus volume, right? So I'm just going to convert my moles to volume. First, by multiplying by 0.03 to get grams, and then dividing by 34.01 grams per mole to get moles. So I'm just going to go ahead and convert my volumes of hydrogen peroxide solution to moles. So I'm just going to erase some of this to get it out of the way. So my 1.8 mils was 0.001588 moles. So my 3.0 times 0.03 this is 0.02646 moles. Erase this, get this out of the way. 3.65 mils. That is 0.03220 moles. And 5.6, which is too much, I found out. Gave me more than 50 mils of gas, so this is not going to be very accurate. 0.04940 moles. And my volumes of O2 gas were 15.5 mils, 28.0 mils, 36.0 mils, and approximately 51. So this is, obviously that's going to be an issue. It went over 50, so I had to, that's going to be an estimate. So then I go to my graphing program, whatever it might be, and I put moles are going to be my X, and remember my volume is going to be my Y. Okay. Is everyone done? Is everyone finished already? I'm just going to go ahead and plot my data then. You can see. Okay. All right, so I've got my data. So I'm going to put moles of H2O2. Here I'm going to put volume O2. 0.1588 0.2646 0.322 0.004. Oops. And then my volumes. And so are we going to be using milliliters? What units are we going to be using for volume?
Milliliters.
Liters.
Liters, right. When we go PIV nerding, we don't use milliliters, right? We use liters. We use atmospheres, Kelvin, moles, and liters. So we got to convert my milliliters to liters. So my 15.5 mils magically becomes 0.0155 liters. You can see there's a little, so it's going to be really easy to make a mistake here because there's all these 0.0s, you know, and 0.00 and 0.000 and all that. So yeah, you have to be really careful that you're getting the units right. So just to liters. Okay. So I want to plot moles versus liters. So insert chart. I want to scatter plot. Oh, looks pretty good, actually. Looks like a fairly straight line. So call it determination of R. And it looks like to pretty much go through 0 too, which is good. So your plot should go through 0. And I think that would have been even better if I hadn't screwed up the last point, because I used more peroxide than I should have, and I went over 50 mils. So I think that's probably why that 4th point is off the line. I probably underestimated what the volume was with 51 mils. It was probably a little more than that. All right, so I want a trend line. I want linear. That looks, man, it looks really good. I'm such a good scientist. What can I tell you, people? So I also want the label. Display the equation on the chart. There we go. Man, so it comes really close to 0. So my slope is 10.558. And so you remember what the slope was when, I'll take this back and put it on the whiteboard. Man, that is a really good result. Hopefully, I don't know if this means anything. Hopefully we'll get a fairly, because I think the y-intercept is very close to 0. And I think our R squared value, which is basically shows you how far off of linear the line is going to be really good too. So here we go. I want to see the R squared. There we go. Yeah, 0.989. That's excellent. So yeah, I think that we have a good chance of this experiment working fairly well for us. All right, so I'm going to go back and look at how this fits in with our work. So from the slope of the line, we had moles of H2O2. Oh, I just thought of and volume. I just thought of a error I made. Anyone spot what it is? What am I plotting? I have made a mistake. What mistake did I make? Look at what I'm plotting and tell me what mistake I've made. No one sees it? What should I be plotting? If I want to determine the value of R for oxygen gas, what do I have to plot? I have to plot the relationship between volume of oxygen gas and moles of what? What do I have to plot? Volume of oxygen versus moles of what? I know you know this. Remember, when we're PIV nerding, so I would need the pressure of oxygen, I would need the volume of oxygen, I would need the temperature of the oxygen, and I would need moles of,
Oxygen.
yes, there you go. Yeah, I need moles of oxygen, but I didn't do that, did I? Because I'm dumb. I plotted moles of hydrogen peroxide versus volume of oxygen. That's not right. It is if there's a one-to-one relationship between moles of oxygen and moles of peroxide, but is that the case? How do I know what the relationship is? What do I need to refer to see the molar relationship between hydrogen peroxide and oxygen gas? Am I just going to have to guess what the molar relationship is? What do I refer to find out what the molar relationship is between a reactant, which is my H2O2, and my product, which is O2? What do I need to tell me what the relationship is between those two things? What have we been talking about since the class started practically? You've always got to balance something. What is it I need to see what the relationship is between hydrogen peroxide, which is my reactant, and O2, which is one of my products?
The chemical equation.
Not just the chemical equation. What kind of chemical equation?
Balance.
A balanced chemical equation. Exactly right. So what is our balanced chemical equation for this? Someone help me out here. So I've got, oops. I've got hydrogen peroxide. Put some catalase on that. And I get oxygen. I think I got some water too, right? That's not balanced. So I got 2 oxygens on the left, and I got 3 of them on the right. So how do I balance this? Is this my relationship? Is it a one mole to 1 mole to 1 mole? Because that doesn't look balanced to me. How do I balance this equation? Somebody help me. I am old and feeble and cannot balance equations on my own. What do I need to do to, if I have 3 oxygens on the right as products, but I only have 2 atoms of oxygen on the left, how am I going to fix that?
You need to add 2 to H2O.
Okay, so if I now I have 4 oxygens on the right, but only 2 on the left, so it's still not balanced.
Put a 2 in front of the H2O2.
Well, yeah, why don't you put a 2 in front of it? All right, okay. Oh, that's right. No, exactly. So now we have 4 hydrogens on both sides. We have 4 oxygens on both sides. Everything's kosher. So this means that I have a relationship of 2 moles of peroxide makes 1 mole of oxygen. So actually, I put twice as many moles as I should have, because I plotted moles of H2O2, and there's actually, I needed to divide that by 2. What would that do to my slope? So if the slope of this line, if the slope of this line is 2, what if I half the value of x? What happens to the slope of my line? Y stays the same. X goes down by a factor of 2. What must happen to the slope? You won't have to do this because you're not dumb enough to plot moles of hydrogen peroxide versus volume of oxygen. You're going to make the correction and plot moles of oxygen. But if my value for X goes down by 2, what must happen to the slope in order for Y to remain the same? So our Y, our volumes don't change, just my values of X do. So all my X's are half. What must my slope be in order to keep Y being the same thing? If X goes down by a factor of 2, the slope must
Go up
by
2.
That's right. Yeah, my slope's got to be twice as much because my X is half as much, so my slope's got to be twice as high. So when I plotted my graph, the slope was Y equals 10, 5, 5, 8 X. So this is my volume in liters. This is moles. And this was the initial slope, which now should be twice as much. So my new slope is 10.558 times 2. So my new slope is 21.116. So let's figure out what that slope is, right? So we think we did this earlier. So if go back to Pivner. So Y is our volume. So I want to isolate volume by itself. So volume is going to be equal to N RT divided by P, right? So this is my Y, this is my X, and this is my slope, M. M is equal to 21.116. So RT divided by P. is equal to 21.116. So my pressure, let me clear some of this out so I can. I want to solve what R is. So let's isolate R. So R is going to be equal to 21.116 times P divided by T. Right? So I want to divide each side by T over P. Well, what's my pressure in atmospheres? Approximately 1, right? So I'll just make that 1. And my temperature in here was 15 degrees C. What is that in Kelvin?
$263.
Close. How do we go back and forth between Celsius and Kelvin? What do we need to do to our Celsius temperature to convert it to Kelvin? Remember?
Add 273.
Yeah. At 273.15. Again, I'm going to use as many significant digits as I can until I get to the end, right? So I'm carrying 5 here. I'm going to carry 5 here, and then at the end, I'm going to round. So R is equal to 21.116 times 1 over 288.15 K atmospheres. So R is 21.116 divided by 288.15. That's not too bad. So my R is equal to 0.073. The actual value, anyone remember what the actual value of R is? So I calculated 0.0733 sphere liter mole kelvins. What's the actual value for R? Do you remember? Actual value of R is 0.0821. And so that is not terrible. I calculated a difference of 10.7% error, which I think is pretty good. I will take that. I mean, let's face it. We're mixing yeast. We're pushing tubes together and trying to put things underwater, and still, with all that, 10% error, I mean, I'd take that any day of the week. So yeah, I think this experiment should work fairly well. So that should be part of your report. Determine what your value is and then compare it to the actual value and give a percent error. Okay? Does anybody have any questions about doing the calculations? I sort of went through that fairly quickly. But remember to plot moles of O2 as X versus volume in liters of oxygen. That will give you the relationship you need between moles and liters, because those are the units involved in the calculation of R.